we're going to go over the parent function for cosine. So it says use your unit circle to graph y equals cos of theta on the interval negative 2 pi less than or equal to theta less than or equal to 2 pi. Use radians as the input and the trig function as the output. Then identify the domain, range, amplitude, and period. So I'm going to sketch the unit circle really quick here on the side. So we have the maximum and minimum for the unit circle values at 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And our corresponding radian values, again, are going to be at 0, pi over 2, pi, 3 pi over 2. Okay, so now if you recall, cosine is our x-coordinates of the unit circle. Okay, so therefore we would have at 0 radians, we would have an output of 1. At pi over 2 radians, we would be at 0. So let's start to plot that. So I'll plot it in green. So at 0 radians will be at 1 here. So the trig function as the output, radians as the input. Okay. Let's write x coordinate like this, so that's to be specific. Coordinate on the unit circle. So at pi over 2, like I said before, we're at 0. At pi, we're at negative 1. 3 pi over 2, we're at 0. And then at 2 pi, we would technically be, we would literally come full circle, right? And our function value should therefore be at 1. So again, the sine function doesn't look like it's not going to look like a v. It'll have some curvature to it. So it'll look closer to something like this. It's like a curvy v, like a valley. Okay. So this is technically one period of the cosine function from 0 to 2 pi, right? And it makes sense that it's one full period because that's one revolution of the unit circle. All right, so let's think about doing the same thing that we did before with sine, number sense activity, approximate values from the unit circle. So I'm just going to flip back, and I just copied it over here. So let's take a look at another unit circle value for cosine that we can kind of plot easily. All right, so let's instead of looking at pi over 6. Okay, because of the fact that our x coordinate would be radical 3 over 2, it'll be kind of messy to kind of guesstimate that value. Okay, so instead of looking at pi over 6, let's look at pi over 3. Okay, so at pi over 3, our unit circle value is going to be 1/2, comma, radical 3 over 2. And remember that cosine is the x coordinate. Okay, so that's why I chose pi over 3, because of the fact that 1/2 is a lot easier to kind of wrap your head around than radical 3 over 2. So now let's kind of guesstimate, again, approximate the values from the unit circle. So pi over 3, take a second. If you were to try to write that as a decimal, it would be just a little bit more than 1, right? So pi over 2 is 3.14 divided by 2, so it's a little bit more than 1.5. So it makes sense that at pi over 3, which is a little bit more than 1, so let's say it's about here, it's about 2/3 of the way to that tick mark, we're going to be at 1/2. Okay, and we can have that same idea and use symmetry to graph its equivalent value from quadrant 2, which would be 2 pi over 3. and the coordinate there would be -1/2 radical 3 over 2, right? Because it's -x positive y in quadrant 2. So therefore, in at 2 pi over 3, so take a second to estimate 2 pi over 3, and you're probably thinking 2 times 3 divided by 3, so it's about 2. So it makes sense. So this is about 1.5. This is about 3. So at about 2, so it's about here, right? A little bit past 1.5. We're at -1/2, like on that coordinate there. And again, we can apply this same principle if we were to kind of do the same thing with in quadrant 3 and in quadrant 4, right? We could use that same idea to get the other values from the parent function. But we have one period. Let's just work with it from there. Okay. So again, coterminal with each of these angles. So from 0, the coterminal angle is -2 pi. So we're going to be at -2 pi, 1. Coterminal with 3 pi over 2. Sorry, with pi over 2, we're going to be at -3 pi over 2. Coterminal with pi, we're going to be at -pi. Coterminal with 3 pi over 2, we're at -pi over 2. Coterminal with 2 pi, we're back at 0. So here is 2 periods of cosine. -2 pi to 0, and then 0 to 2 pi. Okay, so that kind of valley shape is what we're looking for the parent function of cosine. All right, so key characteristics. The domain, just like with sine, the parent function's domain for cosine is -infinity to infinity. The reason why is because I could plug in whatever I want in for my input, any radian value that I want, and I'm going to get an output. The range is restricted because, again, it oscillates between from 1 to -1 and then back up. So our range is restricted -1 to 1, close bracket on both sides, because it can equal it. The amplitude, again, by definition, is the distance from the midline to the max or the midline to the minimum. Amplitude for the parent function for cosine is 1. The period is 2 pi. The symmetry, whether it's even or odd, is going to be, hopefully you guys said that it was even, because there is symmetry about the y-axis, and you guys can see that pretty clearly here. Right, if we were to draw a, well, we really have the y-axis here to act as our line of symmetry. These would be mirror images on either side. Okay, so there's symmetry about the y-axis, and remember the definition for it to be, let's say, recall for even functions, even symmetry. If we were to have x, y as a coordinate, we would have -x, but remain the y value, the output would remain the same. Okay, so let's do pi -1. This is a good example. So xy, if we were to switch the sign of the input, -pi, the output stays the same, right? So it's only the sign of the input that changes, but the sign of the output will still stay the same if a function has even symmetry. All right, so these are all the key points for the parent function of cosine.